Okay, so in this chapter, we're going to be learning about conserved quantities. And so just very simply, a conserved quantity is just like it sounds. It's a quantity that remains constant before and after a reaction. So the main things we talked about are these right here: the conservation of mass, charge, angular momentum, and linear momentum. So we're just going to go into that. So conservation of mass. So conservation of mass is it's a law, because you can't change the amount of mass in the universe. When you get two different chemicals reacting together to create something new, the physical form of the mass changes, but the physical mass of the products and the reactants, the physical mass before and after, is the same. So you've got conservation of mass. Next one we've got is conservation of charge. Conservation of charge has to do with the flow of electrons from different objects. Electrons are like mass. You can't destroy it or create it. It's always just inherent. And so because you can move charges or move electrons from one object to another, but you can never destroy them. It's just a simple transference. And that's what the conservation of charge is about. Now the next one is angular momentum. That's a little bit different. So up here you can see angular momentum is equal to mass, which is m, times r, which is radius, times velocity. So I'm afraid I don't have it with me right now, but let's imagine that I'm swinging above my head a ball. And so let's say that we've got these three numbers and the ball is going a certain speed. The length of the cord that I'm swinging with, or the radius, has a certain length, and the ball that I'm swinging has a certain mass. So when you multiply those three numbers, when you multiply these three, you'll get a certain number. But let's say that I shorten the cord while it's still moving. That means the ball is going to start swinging faster because the angular momentum has to be conserved. So if I shorten the length of this, that means the velocity has to go up. If I make this longer, if I make the radius longer, that means the velocity has to slow down. And so angular momentum is always going to be conserved. So if I'm swinging it fast and then I make it shorter, it's going to go faster. If I'm swinging it fast and I make it longer, that means it's not going to go as fast. So angular momentum is always conserved. Now, last one we're going to talk about is just linear momentum. Linear momentum is a little bit simpler. You've just got mass times velocity, and that's always conserved. And so, very simply, let's say we've got 100 kilogram object. We've got a 100 kilogram object going 10 meters per second. It runs into a 1,000 kilogram object. We need to ask the question, how fast, if all of the linear momentum is transferred from this object to the bigger object, how fast is it going to go? Well, linear momentum has to be conserved. So if we do this one, that means it'll be 1,000 kilogram meters per second. So if this weighs 1,000 kilograms, that means if all linear momentum is going to be conserved, this is going to be moving 1 meter per second. Because the number at the end of this has to be the same number at the end of this. Linear momentum is conserved. When it comes to things like explosions, so for instance, rockets and stuff, we shoot it upwards and then it blows up. That just means the mass and the weight of all the pieces, the mass and the speed of all the pieces is going to equal the mass and the speed of the original piece. That's for a rocket blowing up in the air. Now the last part of this is linear momentum at high speeds. All right, so this part is a little more complicated, so just kind of bear with me as you go through it. So the question we need to ask ourselves is, we know that a lot of weird stuff goes down when we get to relativistic speeds, or speeds that are close to the speed of light. So if nothing can go faster than the speed of light, then how can linear momentum be conserved? And I'm going to try demonstrating that to you right now. So let's go with our regular numbers. The speed of light is equal to, so c, which is the speed of light, is equal to 3 times 10 to the 8th meters per second. So let's imagine that we've got something that weighs 3 times 10 to the 8th kilograms. and it's moving at 1 meter per second. That means the linear momentum of this is going to be 3 times 10 to the 8th kilogram meters per second. If all of this, if we somehow make it so all of the linear momentum of this quantity is transferred into something that's only 1 kilogram, what's going to happen? Well, technically, if this is 1 kilogram and all of the momentum is transferred, that means the speed of this would have to be 3 times 10 to the 8th meters per second. But we already know nothing can go that fast except light. So how can linear momentum be conserved? How can it be transferred? When it's transferred, how can it be conserved if nothing can go that fast? The answer is with relativity. It's not going to go that fast because at relativistic speeds, it's going to get heavier. So this will actually get significantly heavier, and so it'll get really fast if all of the linear momentum is conserved, is transferred, but it won't get the speed of light. So what is 1 kilogram will actually be much heavier, and it'll be much slower than 3 times 10 to the 8th. So at the end of the day, linear momentum is conserved because of relativity. So I hope this made sense, and I hope you guys don't struggle with it too much. But just always remember, momentum is conserved. It has to be transferred. So if I run into something, I need to transfer my momentum. It doesn't just go away. Thanks.